Yeah, I will talk about parent grain reconstruction again, but this year is not so much about yet another algorithm or something, but more about with the existing algorithm. We notice that a lot of you might be using this with parameters that are kind of taken as default parameters. And I would like to maybe put some light on that there are actually parameters that we can actually tune towards the microstructure we're looking at, and we can actually significantly improve the parent grain reconstruction by looking at this. This one is not working.
Maybe it's even better if you use the mouse because the online people can't see.
Oh yeah, I have to respect the online people. So this is again a collaboration with Tuomo Nyssen, Aste Gasta, and Ralf Hietscher. So, I mean, Tuomo already did a little bit of a recap, so I'm going to skip over this a little bit quickly. But parent grain reconstruction simply concerns the problem that we have a microstructure, for example, at high temperature. This here would be austenite. And that during cooling, for instance, we get a phase transformation and like a fragmentation into a lot of child grains of a different phase. And parent grain reconstruction then aims to go back from this microstructure that we might have acquired with our EBSD system to reconstruct the parent microstructure that used to be there at high temperature. We can use visual clues. For example, here there's actually a quite, I mean, Tuomo said it's a mess, but there is actually some kind of hierarchy in here. And if you tune your eye to it, you can actually discern where are the prior parent grains. But algorithmically, we're actually looking at the misorientations between the different child grains and how they correlate to the orientation relationship, which is somewhat of a, let's say, representative misorientation for the phase transformation. And if we look at just one example, so here we have one small parent grain with some child grains. We can then look at all the orientations that are present, determine the misorientations, compare this with a characteristic misorientation of the orientation relationship, and thereby discern, very simplified, the parent orientation. And once we have that, we can of course then reassign it, and voila, we have a reconstructed microstructure. And from there on, we can do lots of other analysis, like for example, variant analysis. So the motivation today is that parent grain reconstruction actually has become quite a popular MTEX feature, which we're of course very pleased about. And usually the route of entry to parent grain reconstruction is either the MTEX documentation or OR tools. And OR tools is a toolbox for orientation relationship discovery, which kind of helps you to kind of with very simple functions, visualize a lot of these things very intuitively. And those scripts that we kind of ship with this documentation, they usually have some assumptions about default parameters, and they're usually set as a trade-off value that kind of work for most microstructures. But you might also have quite challenging cases. This here, for example, is isothermally formed bainite, which is similar to martensite, but it also involves a little bit of diffusion, and it's actually not so straightforward to reconstruct this kind of microstructure. There's a very fresh paper out on this topic from 2024. And the cool thing about this paper is that they used a high temperature setup where they actually could measure the microstructure before the transformation at high temperature, as well as after the transformation. And this is, of course, a really cool data set, which they made openly available, thankfully, to check how well those reconstruction algorithms actually work. And in the paper, Aztec crystal was compared against MTEC. The conclusion was in the end that both were actually quite good to get the prior austenite grain size and also the texture. And they also said that the annealing twin orientations were discovered quite well, but some of the morphologies of the boundaries were maybe not as good as they should be. Just to show an example here, for example, we have an annealing twin. In Aztec, it's almost completely absent. In MTEC, it has like a weird shape, which I refer to as a curly fry or something like this. Then we have other instances, for example, this here is falsely reconstructed and so forth. So it's not really perfect, even though it maybe does a quite good job. This, of course, we looked at this data set and looked what kind of parameters did they use, and they've kind of removed the standard parameters, and it kind of begged the question, can we actually do a dedicated parameter choice for this data set to get better at this reconstruction? And this there may be some general guideline that we can recommend to get towards the best parameters that you also can use for your microstructures. And that's something I want to cover today. So again, the entry points usually over phase transitions in the MTEX documentation, martensite parent grain reconstructor, or following this OR tools toolbox. And the steps involved in parent grain reconstruction are usually grain reconstruction from EBSD data. So that's the child grains. Then we specify an orientation relationship. We set up the variant graph. So we use this variant graph algorithm in this work. Then we cluster the variant graph. we calculate the parent grain orientations from the votes that have been decided by the variant graph, and then we can do several things in post-processing, like refining this further, filling, merging, analysis, and so forth. So I'm going to go into each of these steps today and look at what are the parameter choices that are crucial in these steps. And all the figures you see today, they actually were created with some scripts that are made openly available on the OR tools repository under sub-folder tutorials, parent grain reconstruction, parameter optimization. And I made sure to have both only MTEX syntax and also OR tool syntax separately, so you can choose the one that you prefer if you want to dig into this. So let's start with the first step, which is child grain reconstruction. And a lot of MTEX users are familiar with these 4 lines, which basically means we kind of reconstruct the grains with a threshold value of 3 degrees, take out all the grains that are pretty small, and then we take the remaining data to then reconstruct the grains again. In the end, we might want to smooth the boundaries a little bit, and voila, we have reconstructed grains. And this just visually looks quite good, right? This is the magnetic microstructure you saw earlier. When we then do the reconstruction, we get here, and I still kept the original outlines of all the child grains in place. And also visually, this looks quite good to start with, I would say. Then, of course, if we have now the luxury of having a validation data set next to this, and we can then maybe identify some regions where it didn't work out so well. For example, again, this curly fry shape is here again. The green grain is a lot smaller than it's actually supposed to be. And if we look closely, we actually are constricted by the shape of the child grains that have been reconstructed in this step, because here actually this annealing twin, we cannot really get the shape right, because already the shape of the child grains determines which color we can fill in here, and we have actually no chance of getting correctly if we don't reconstruct the child grains in a better way to start with. So an intuitive way of going about this would then be to maybe reduce the threshold. So here we reconstruct the thing at 2 degrees threshold, and while we do not get much better here, actually this one, for example, just by changing the reconstruction, the child grain reconstruction threshold, now looks a lot more like what the validation data set shows. We can be more aggressive and go down to 1 degree. Also, this worked actually quite well with this data set. Might not work for every data set. And we can now see that also this green annealing twin, that the morphology suddenly looks pretty much like what we want to have in the validation data set. So there's a clear improvement by actually cutting down this threshold value and kind of refining the child grains a lot more than what we previously did. Of course, we can go even more aggressive, and then we hit a noise level. So at some point we have to stop, because this reconstruction, of course, does not really, lead to any good outcome. So one has to kind of figure out how aggressive can one be about refining the child grains. Then the last way of doing this, and something Astegasta has tried, is to use this unit cell command or parameter in the child grain orientation. And this basically helps us to not merge all these unindexed regions that we usually have into the surrounding grains. So basically just treats them as that territory that should not be touched, which means we get a lot of fragmentation of the grains, but which is maybe not so visually pleasing. But actually in this case, it's quite helpful, as we're not starting to merge grains that maybe shouldn't be merged together. And now for the first time, we can actually see this annealing twin also being reconstructed quite nicely. So from this, it should be quite clear that careless reconstruction of the child grains may lead to poor reconstruction of the annealing twins and small parent grains. So we really have to take care of this. And grain reconstruction should, for such challenging data sets, be as refined as possible, of course, without reaching a noise level. And of course, one could take this even further and think maybe one could drop grain reconstruction entirely, because as soon as we basically start reconstructing grains, we're already throwing away a lot of information, right? We have so much information in the EBSD data. Maybe we can use this to reconstruct the grains. Now looking at a different data set, this is a martensite map kind of from the MTEX examples. This is the conventional reconstruction result we get from the parent grain variant graph reconstruction algorithm. And this is kind of a prototype variant graph that operates on EBSD level. So we cluster EBSD pixels instead of grains. What we see here actually is that the annealing twins that we see here are actually nicer refined on EBSD level, also here. But then on the downside, you can see that there are a lot of colorful patches that are kind of being created by some kind of noise level in the data. So going local in determining the orientation of the parent grain has its benefits, but it also comes with drawbacks, and there has to be some kind of balance. And this is kind of the ongoing research, if this is actually useful to do or not. So going further to the orientation relationship. So in MTEC, we kind of call this parent grain reconstructor class with the EBC data and the grains, and then we get this job object up there. And if we just do job.p2c equals some orientation, we can assign an orientation relationship to the job class. Here, usually a good starting point for these sitting microstructures or bainitic is Kodimov-Sachs. And we can then use this algorithm calc parent to child to further refine the orientation relationship based on the misorientations that are actually present in the microstructure. And this is according to an algorithm that Tuomo has developed some years ago. A good way to then visualize how well this orientation relationship fits to our microstructure is to plot this child-child grain disorientation diagram. And this basically means, for example, given the Nishiyama-Wasserman orientation relationship in yellow, how well does this orientation relationship fit to the misorientations that are present between all the grains in our microstructure. And the further we have to the right, the worse a fit we have, of course, meaning that Nishiyama-Wasserman is not really a good descriptor of the actual orientation relationship. Kodimov-Sachs is a bit better, but we can get a lot better by actually iteratively refining this orientation relationship. So this is a very good indicator, and if you have a data set and your distribution is somewhere all the way to the right, you should ask yourself if you at all have an orientation relationship. So this gives you a good indication of how successful you're going to be with your reconstruction. We can also plot these values onto the boundaries themselves, so we can get kind of this orientation for each grain boundary, and then we can use it to tune the edge alpha value of the grain boundaries, which means that the darker boundaries here correspond to a bad fit with the orientation relationship, and some of them are almost transparent, meaning that they fit very well. And if you then can see some obvious outlines of parent grains, then you're on a good path towards a good reconstruction. Within OR tools, we have this function plot map GB misfit. Does the same thing, just the plots look a little bit different. So here we use a color scale to indicate the misfit. And if you then compare different orientation relationships, this one is the fitted one, we can actually see nicely the outlines of the parent grains, where, for example, Nishiyama-Wasserman or Kodimov-Sachs, not so much. So this would not lead to good reconstruction, for example. And this is something you should visually check when you do a reconstruction. How well does the orientation relationship actually outline the grains that I want to reconstruct? So the next thing is then, no, it's not the next thing, sorry. I'm going to talk about two parameters that one can set while doing this iteratively. So this is the iterative refinement of the orientation relationship function, and there are some values that are usually set as defaults, but you can access them and change them. For example, one of them is quantile. Quantile is usually set to 0.9, and that usually means do not consider the worst fitting 10% of the grain boundaries for estimating the orientation relationship. So if you say this is 90% of our data, then this data here is discarded for the fitting procedure to get the optimized orientation relationship. On top of that, we also have the threshold value. It's by default at 10 degrees, and that basically says if the misfit is higher than 10 degrees, also discard this data for optimizing the orientation relationship. So you have two parameters with which you can actually play which data goes into the refinement, and the algorithm will actually look at the sharper criterion and enforce that criterion to figure out how to refine this orientation relationship. In our case, when we look at this distribution, we take different quantile values, for example, not much changes actually. And we can again plot these results onto the boundaries. We can see for different quantile values, the outlines look all fine, more or less. But just to show you that this is real, if we put the quantile value to almost 1, then we basically almost take all the entire data into account for fitting the orientation relationship. And suddenly our distinction does not look as good anymore. Because suddenly we also take, let's say, the parent boundaries into account, which are not really, which are not part of the orientation relationship. And usually a good value for you, if you want to do your own reconstruction, and to choose the quantile smaller or equal to 1 minus the estimated fraction of the prior parent grain boundaries. Here, for example, we can maybe say it's less than 10% because we have a lot of internal structure. Therefore, all these values give, or apart from this one, of course, give a quite nice orientation relationship. But if you have almost no internal structure and very small parent grains, you probably need to use a smaller quantile value to actually get a nice orientation relationship. So now we get to setting up the variant graph by this command, calculate variant graph. I'm not going to go into detail about how this graph works. That's a past presentation. But in essence, if we have a grain graph, we take each of these grains you've seen before, the child grains, and we give them one node in a big graph. And all the neighbors are going to be connected by edges which are then having assigned probability values on how likely they are related by the same parent grain or belong to the same parent grain. And then by kind of iterating over this graph, we can extend this to second neighbors, third neighbors, and so forth. The variant graph kind of does the same thing, but it has separate graphs for each of the possible variants. But essentially, what's important for you to know is that also here, the probabilities we assign to these edges are quite important as to how effective and how successful the variant graph will operate. And this probability is actually directly derived from this disorientation angle that we saw earlier. So we have this disorientation angle to the orientation relationship, and then using those commands threshold or parameters threshold and tolerance, we can then design a probability function that kind of reflects a value between 0 and 1 of how probable it is that a boundary is part of or connects two grains that are part of the same parent grain. The function is an arrow type function, and this threshold value that we set kind of decides where is this function 0.5, and the tolerance value kind of shows you how smooth this function is going to be. But it's a lot easier to actually show this on real data. So we look again at this disorientation distribution from earlier on, and we can see if we take a threshold value of 2.5, a tolerance value of 2.5, that we're kind of cutting into the middle of this distribution that we know is somehow related to the internal part of the grains. And we still see the outlines of the parent grains, but we can also see a lot of dark, low probability boundaries inside of the grain, which is maybe not ideal. And maybe to note, this is the default parameter in the parent grain reconstructor script. What we can do to mitigate this is, of course, to go up in threshold values. So we push the whole distribution or probability function further to the right, and also chose a quite steep tolerance then, so the curve is a little bit more, less flat. And here we already get a lot better distinction between the prior parent grain boundaries and the interior of these grains by the different probability values. Something you should not do is use a very high tolerance value and a very low threshold value. In this case, you basically don't hit 1 in probability when you are at a perfect match. So I think this is kind of being normalized out later on, so it doesn't really matter so much, but this is not a good choice. And equally, if you have a distribution like this, if you then cut it very, very sharp, of course, you're going to have a lot of very low probabilities for belonging to the same parent grain, even though we obviously know, at least I do, if I look into microstructure, that these regions here should be the interior parts of the parent grains. So tuning this is quite important actually when you do a parent grain reconstruction and you have some challenges, because this is basically what the variant graph works with, and if you give it some rubbish to work with, it's not gonna produce anything nice. Then there's one, maybe to also note that calc variant graph by default has threshold 2 and tolerance 1.5. This is very close to this setting, so if you don't tell the variant graph anything, it's probably not going to give you a good reconstruction for this data set, for example. Then there's one last parameter set that I would call Tomo Speciale, because I asked Tomo about his favorite, let's say, parameters for Grain reconstruction. He said, I always use threshold 5, tolerance 2, and it gives really good results. And one can see that actually this probability function nicely curves around this distribution here and really gives a nice distinction between the outlines of the prior parent grains and the internal part. So maybe Tomo's onto something here.
So please use that as a reference. Tomo Speciale.
Yeah. So now let's look at which reconstruction, let's say, result we get from these different parameters. And we basically now chose all the clustering afterwards to be standard and the same. We can see in those lower two cases that were not really ideal, that actually reconstruction also suffers quite a lot. This here was a standard parameter set, which gives us a quite okay reconstruction, I would say. Actually, this one I think gives us a little bit better reconstruction because more errors actually have been filled with more confidence that this is the right parent orientation. And now look at Tomo Speciale. We can see that we have actually quite nice reconstruction, like the confidence is quite high everywhere, so everything has been filled out and it intuitively looks pretty well refined. So I think these are actually good parameters for this data set at least. Now the next job is to cluster the variant graph. So we now assigned this probability function earlier to kind of tell it what is likely, what is unlikely, but now we have to go for the clustering algorithm. And the clustering algorithm then starts, as the name suggests, clustering together the grains that belong to the same parent grain. So if we have a lot of connectivity in the beginning, it basically starts to enforce some of these connections and cut off other connections until we have some, let's say, clusters that say, okay, this is a parent grain, this is a parent grain, and so forth. We can just run this without any commands, but again, there are a lot of options that we actually can set. One of them is the inflation power. The inflation power is the small alpha parameter here in the inflation part. And what this inflation part does, it actually looks at all the probabilities on these edges. And by putting a value larger than 1, we actually increase the probability of already probable connections. And we actually start cutting off or reducing probability of not so promising connections. Basically, the larger this inflation parameter, the more aggressively we're going to start cutting off those edges early on. We can actually see this in this graph up here, where we have the variant graph with different inflation parameters. This is the number of non-zero edges, so edges where we actually have a probability value. If we use this parameter set is very high, after a few iterations, we basically start cutting off a lot of information, and we kind of say, okay, that's it. We don't want to explore further neighborhood relationships or anything. On the other contrasting end, if we put it to 1, basically we are not really inflating anything, and we're kind of building up more and more and more connections with higher order neighbors. And there's actually, as we see later on, some kind of benefit to that as well. Then the next parameter is number of iterations. So for how long do we actually want to run this? Because with each number of iterations, we actually expand by 1 order of neighbors that we look at. So if we run 20 iterations, we actually go onto the 20th order neighbor, and that might not always be beneficial, as we will see. So let's maybe look at these parameters one by one. Now we change the inflation parameter from 1.4, 1.2, 1.1, 1.05. We can definitely see cutting off too many edges in the beginning with a high inflation parameter sets us up to failure. And from all these things, I guess this one is still the most promising one, which is also the default setting that we usually have in this clustering function. Then there's another Tomo Speciale data set, which is alpha 1.0, number of iteration 5. And this actually also gives quite a good reconstruction in this case. There's some regions where it's not quite sure. So everything with a probability lower than 0.5, we kind of haven't reconstructed here yet. But usually with a little bit of post-processing, you can fill this up quite nicely. What about the number of iterations? If you now look at the most promising ones, was inflation parameter 1, inflation parameter 1.05. What if we step a number of iterations? So 5 is usually somewhat of a standard value, maybe. If you go to 8, we actually get more areas filled in with quite confident, let's say, reconstructions, I would say. Then if you go to 10, it gets worse again. So this can actually be explained by that more iterations are not always good, because you kind of spread out the information further and further to higher order neighbors. And at some point, this might actually reduce the quality of your reconstruction result. So 8 is actually a quite good value for this data set. I encourage you to play with this for your own data set. On the other hand, if we start with 1, this is catastrophe, because when you look at the direct neighbor, 2 gets a little bit better, 3 somewhat, but the final answer for this data set was inflation parameter of 1, number iteration 8 gave a really good reconstruction. Compared to the default settings that we usually use, this is quite an improvement, I would say. So alpha 1 is actually quite good because we don't throw away any information, but of course you will also use more memory. So if memory usage is not a problem, this is quite recommended, I would say. And a relatively low number of iterations is useful, but it really depends on how refined is the interior of your parent grains, of how far you want to explore the neighborhood in your microstructure. So here, this really depends on your data set. So there are now some final steps in parent grain reconstruction, which is we can use this command calc GP votes, reconsider all, kind of fill out the last remaining areas that have not been successfully reconstructed by comparing it with already existing neighboring parent orientations. This is usually very effective if you only have a few patches that you need to fill. Then we can merge all the similar grains in terms of similar orientation, and we can remove very small grains by just merge these inclusions. And then we kind of have the final reconstruction. So this is my last slide, and we can now compare the validation data set versus the reconstructed data set that was published using the default parameters and the reconstruction that uses optimized parameters. And I do think that the difference is quite significant. If you look at this region, for example, this is almost spot on now, whereas before this looked a little bit weird. Also, this region here looks a lot better. because this pink grain is suddenly reconstructed nicely, which means this might be an annealing twin that actually now is fully captured. Of course, there's some things that are still not there, like these small annealing twins, they're still not being reconstructed, but in general, the parameter optimization really has paid off. And if you have challenging data set, I can really recommend you to dig into this as well to get the best possible reconstruction. For those challenging cases, just to summarize, properly refine the child grains as much as you can without hitting the noise level. Validate that your orientation relationship choice is optimal by looking at these orientation profiles. Define a probability function that suits your disorientation profile that nicely outlines what you think are the parent grains. And cluster the variant graph at a likely low inflation factor to the optimal number of iterations, which is something you have to play around with. Lastly, we had the luxury of having this validation data set, which we again thank you also for putting up online. But I think you can even do this optimization without having a validation data set, just by looking at those parameters and actually looking at the outcome, which kind of intuitively see when it gets better or worse. And lastly, if you need the best parameter sets for martensite Bena, you should ask Tuomo, because after OMO optimization, I basically came down to the same parameters that Tuomo shared with me. So that was really good.